That was joking. Can I have some of this? Oh, okay. You have hot water in this? You're crazy. You put warm water in this? Oh my god. Yeah, that's fair. That's
Matthew, there's water right outside.
okay. Okay, that's too far. But maybe a little bit. Oh my god, can I see those cookies? Is it like...
Please.
Is it just... I'll take some later.
Any questions?
Yeah.
Okay, there was a request to change the date for the last quiz.
Oh, yes.
He's gonna make it on Thursday.
The last quiz, because then we have two stacks on the So if you change it, that's
I love 280.
So right now,
Oh,
we have last quiz on
Shut up, I'm talking.
and the week before that we have the quiz on master. So I'm just trying to see if that's still the case. You want to change it? How many people want it to be changed?
To what? Wait, to what?
The last
I
place
always
is
know what
Tuesday.
you're getting into. Okay, so quiz 5. I think that's the last day of classes.
Yes.
And we cannot put it after that day. Right? And we have a very important topic to cover. The outcomes are very, very important. So, and then we are going to miss this lecture because I made an announcement about that. Right? So here's my proposal. Then we move quiz 4 to this day, and quiz 5 to this day.
Wait, so there's no quiz.
Wait.
No, you move it.
Shut up,
There's class on Tuesday.
This is the Tuesday after Good Friday, sorry, after Easter Monday, right? And we do not have a lecture on that day, but I can have a TA to come and be here for the quiz. So we move the quiz to this day, we keep lecture day on Friday opens, and we move this quiz to this day, use half of the time for lecture there and half for the
Double up on the hall.
So will that work?
So we would go Good Friday, Quiz 4, op-amp, non-idealities, Quiz 5, and then electronics history.
Yeah.
Yeah, okay.
So do you think that's going to work? So this is actually helping us with some of that lost time we were in the lecture and missing anything.
Tuesday, I do both places.
I wanted to do that.
Okay, so what I'm going to do is that I make a, see this is the issue, that because we're changing this mid-semester, I have to have everybody's approval. So I'm going to post an announcement about this on Canvas, put a quiz there, and then you go and choose yes, no, right? Yes, no, or I don't care, maybe 3 choices. And we have to have yeses and I don't care, right? So if there are no's, then it means that we can't do it, okay? Because these dates are decided at before the semester begins, according to all the classes that we think most of you are taking and the notes for each one of them. So changing them mid-semester requires approval from all of you guys. So if a couple of guys don't want to do it, then unfortunately we can't. So I'll put up that quiz soon, and then we'll see what happens. Okay? Changing your quiz date,
That one.
we thought it would be easier, but unfortunately. All right. So let's get back to our discussion on MOSFETs. So we looked at this new nonlinear device. Where we usually show 3 terminals, but we know it has 4 terminals. The body terminal is usually not shown unless you explicitly show it to source on integrated circuits. And for discrete devices, it's usually shown as empty. So it's not normally shown. We treat it as a 3-terminal device. We said there are 3 operating regions. There's cutoff and trial. Cutoff, the device is off, ID is 0. We already know that IG is always 0. Small or large signal, because you're looking at an insulating layer between the gate and the channel of this device. And because of that, ID is always equal to IS. So for transistors, sometimes we say IC, IE, because there is a small difference between them in active region. For this device, no matter the operating region, ID and IS are equal. And then there are 2 types. You have N-type devices and similarly a P-type device. For the P-type device, the PMOSFET, again, similar situation, IG is always 0, ID comes out of the drain. For NMOS, ID goes into the drain. The device can be in trial region where it acts as a variable resistor, a controlled resistor whose value is set by, so if the drain source voltage is small, you can estimate that RP from this equation. So there is an RDS, let's call it RDS, the drain source resistance. For small VDS, and then if it is not super small, VDS is not super small, then you have a little bit of nonlinear. So that's for trial region. You can use it as a controlled resistor. It's a resistor whose value is set by voltage. It's great if you want to make something automatic. It doesn't need a human to go there and turn it off. You can decide on the value of the voltage using, electronics logic. This is in trial, so it's a useful region in analog electronics as well as digital electronics. And then we have our favorite region for analog electronics, which is active or saturation. Region for an NMOS, and writing the equation for NMOS, PMOS is very similar. Your equation for the drain current is given by this expression. Okay? And you can see that it is not linearly proportional to VGS. That gives you an opportunity to have chance conductance, to have something that does more than a linear controlled current source, but it's a controlled current source. Right? So the value of current ID is set by the difference between VGS and VTH. Then we showed that there is a small signal model for this device, and it's actually simpler than what you have for a BJT. Like BJT, you have the GM value, change conductance value. And this GM value can be found from a few different equations, but they're all equivalent. They're all reducing to this. So unlike BJTs, where once you chose your, let's say, current, your bias current, your GM was fixed, for MOSFETs you have a couple of knobs to turn, let's say. So W over L is one parameter you can change for a given VGS minus VTH to change GM, or for a given W over L, you can play with VGS minus VTH to get the GM that you need. Okay. Now, one topic we didn't talk about, or didn't cover, is channel length modulation. So I'm just going to very briefly talk about this and move on. Because again, for discrete devices, it's not as important. And discrete devices are what we're focusing on. So for IDVDS here, we saw that it looks like this. Okay. So after you hit, so over here initially you are in the trial region, and then over, let's say, at some voltage here, VGS minus VDS becomes equal to VGS minus VTH. This is the edge of your saturation region. And then after that, your current does not respond to changes in VDS. You have a current source between the drain and source of this device. In reality, like BJTs, that's not what you get. For BJTs, again, if you remember ICD-CE, we like it to be flat, straight, parallel to the VCE axis, but there is a little bit of slope to it. And for MOSFETs, it's the same situation. So in reality, instead of having that straight line, you get a little bit of slope, a little bit of dependence to VDS. HID. Right? So ID, as we increase VDS, ID will increase slightly as well. The reason for that increase is actually similar to the reason we have for BJTs. So when you have a MOSFET and you have your P and N region, sorry, let's say P MOSFET and N regions for drain and source. Let's do the drain at the right side that we usually do. So we said at the beginning of saturation, what happens, or active region, what happens is that the channel that the draining pinches off. So you don't have a, let's say, a nice looking stripe here, but it's a some sort of this little bit of a slope to the depth of that channel. So it starts from something at the source end, depending on VGS minus VTH, or depending on VGS, and pinches off at the drain end. At the drain end, therefore, you have the reverse bias diode. Right? So over here, you have the reverse bias diode. And as we increase the drain voltage, if you go back to the discussions, or if you remember anything from the discussions we had from the diode section or BJT section, when you reverse bias the diode, the depletion region width gets larger. Right? So as you increase that voltage on the drain side, your depletion region ACP becomes a little bit larger. So your channel will pinch off here instead of right at the drain. It's as if your channel is a little bit shorter, right? And because a shorter channel means more current, right? Where is it? This one. Because a shorter channel means more current, you get a slightly more current through this device. Okay? And it's actually linearly proportional to that. This is very important for integrated circuits, and especially advanced technologies where you talk about anything after 90 nanometers. This is a huge pain for integrated circuit designers because this dimension, this length is really small. So any change, any small change in the depletion region width here is going to affect the current for a bit. For discrete devices, it's not as big as a concern. If you want to take that into account, usually DC we don't. We don't bother with that when we're doing the DC calculations. But for AC, if you have your small signal model that's shown here, you add a resistor RO, whose value is found from, there is a device parameter called the channel length modulation factor. Then you can find it from that. Right? So you add one component here to your model that takes into account this dependence of ID to VDS. See, that's VDS. You have a little bit of slope plus an offset. GMVGS gives you the offset. The slope comes from the resistor that is in parallel with your curves. For this course, for what we are concerned with, for the typical application that you will be dealing with, I'm going to ignore it. So I've talked about it in slides. Book goes into details regarding calculations we talk about, but for practical cases that we are dealing in this course, lambda is approaching 0, meaning that RO approaches infinity for RO. So any equation that we see in the book that has RO, put an open circuit or infinite resistance for it, and it reduces to what we have so far. Okay. So, we have already seen the large signal model. we've done a few calculations based on large signal model, a couple of circuits we looked at based on large signal model. We actually solved a small signal circuit too, and we showed that the circuit can give you gain. At least magnitude-wise, you could get an output voltage that is larger than the input voltage. And we are moving to it can be an amplifier. So today we are going to talk about amplifiers. And like BJTs, the first thing you need to do is to bias your amplifier, to set the ID that you want in order to get the GM that you need for whatever amplification factor that you have. For discrete devices, life is easy. So your favorite biasing technique is H biasing. So I'm not going to put anything in the drain terminal, but you can do that if you want. You may have a resistor here, right? So this is our favorite and well-known H bias. Right? So for discrete devices, this is very similar to what you do for BJTs. Good news here is that the analysis is simple. Because for BJT, what you needed to do if you had, let's say, an NPN device here, you had to find the Thevenin equivalent circuit of the resistor combination on the left side, take into account the base current that goes into the base, to figure out how much of the voltage produced by this voltage divider will appear at the base of the device. In here, life is easier because IG is 0. You can go and make your Thevenin circuit, but there is no voltage drop across the Thevenin resistance. So you don't really have to go and do any of that. All you need to do is to right away calculate this Vx. Let's just call it Vx. Vx equals RG2. A voltage division, in this case, they have one supply, but if you have two supplies, between two supplies. And that gives you the extra, because IG is 0. So once you have that, the rest is something we've done before. We can run the KVL from the gate to ground, and KVL tells you that Vx equals VGS that we have between the gate and source. And the difference between this and BJTs is that for the BJTs, if you wanted to use the physical model, you had an exponential relationship between ID and VBE, or IC and VBE, that you needed to go through equations to solve. But for most cases, most situations, we assume that VBE does not change, or did not change much with, let's say, an order of magnitude change in current. And that made your life easy, because right away you have a number you could plug in here and find IC right away, or ID right away. In this case, that's not the situation. So you need to use, assuming the device is in active region, you need to use the equation that relates the voltage across the gate source terminals and ID, and we have one equation for KVL. Vx is a known number, you need to find ID and VGS. So two equations, two unknowns, you should be able to solve this. Look at the parameters that is available to you. Okay, so these MOSFET circuits, there are quite a few of them that are bistable. They can have two stable points, right? So the quadratic equations we solve, sometimes they give you two answers that are both valid. And in many of those circuits, one of the answers is 0, right? So ID 0 gives you one answer, and some ID 0 gives you one stable answer, and there's some other ID that you normally want, which gives you a different answer. And then you have to come up with techniques to make sure that you don't get ID 0. For most of circuits like this, there's only one valid answer. Okay? As long as your V gate, Vx, is larger than the threshold voltage of your device to turn it on, right? And as long as your drain voltage is not so low to put the device in trial region, you get one valid answer if you solve this combination of equations. Now, I usually like to rewrite these two in terms of VGS and solve the quadratic equation based on VGS. Right? So let's call this Kn. This is also known as Kn, the technology factor. Right? This whole thing, I'm going to call it 4 constants. It's a constant at the end. So let's call this Kn. And what I can do is I can find ID from the first equation, so it's Ex minus VGS divided by Rs. Okay? And then you have one equation, quadratic equation of VGS. This equation, once we solve it, will give you 2 VGS values. Okay? So you get 2 values for VGS1 and VGS2, and then the reason I like to write it as rewrite the equation as a function of VGS is that right away you can see which one of these VGSs is valid. One of them will be larger than VTH, the other one will be smaller, and maybe even negative. Right? So pick the one. And then once you have that, you can go and calculate that.
On the quiz, can we use like an online calculator for the quadratic?
Good question. I'm going to make sure you can.
What?
But why do you need a quadratic calculator for what? For the equation?
Yeah, just because it's easier. I mean, that's how we've been.
No, so for, a lot of your calculators can already do this. That's fine. Solving the quadratic equation is not something that I should test you.
Okay. So you don't care, right?
Can I write code?
Write both answers and say which one you pick.
Okay.
Right? So if you do it online or if you do it on your calculator, that's okay. It doesn't matter. But you should know how to solve the quadratic equation.
Yeah, I can do it. I can do it, but it's.
Sure you
Yeah,
can.
just in case it comes up in an interview. You should know. Okay, so once you have ID, you don't do your rest of your calculation. You make sure the device is in active region, and then you're done. Okay, so that's that. There is another alternative or a second biasing technique that is possible for discrete devices. Rarely you see this, but it is similar to what you have seen again for BJTs. Right? And in this case, again, like VJTs, this device can never be in trial because your VGS is equal to VGS, or your VGB is 0. VGB 0 means that your VGB is less than the threshold voltage, therefore the device has a channel at the drain. So as long as VGB is larger than your threshold voltage, you're fine. Problem with this is that unlike BJTs, and actually if you want, you can add a resistor here too. And you often see a resistor, right? And you may ask, if the current through that resistor is 0, why do I want to have the resistor?
To drop the voltage?
There is no drop of voltage if the current through it is 0. It doesn't, there is no voltage drop across.
With just in case, like. What if you pass AC through there?
Yeah, it's for AC performance, right? So if you want to use this as an amplifier, we can analyze it. Let's say a common source amplifier, right? You apply your input to the source, given this, take the output from the drain of this step. And if you short the gate and drain to each other, then you don't have any gain. The input just appears at the output. Right? The transistor is bypassed. So this RF will prevent that. Separates the input from the output. Doesn't do anything on the DC. Solving this is, again, similar situation. You write your KVL. You don't go across the drain source terminal. That's a no-no. If the device is in active region, you have a current source. You go around it, right? So your KVL tells you VD is IBRD, and then RF does nothing because it's IGRF, IG is 0, plus VGS. You may have a resistor here, you just add it to your equation, so IGRS. So that's your equation, and then you have the device equation. Okay? So similar situation as before. Again, you have a quadratic equation. I solve it as a function of VGS, you get a value for RT. This one is not used very often as a biasing technique. Again, similar to BJTs, H biasing gives you a lot more flexibility in terms of what you want to happen at the input of your circuit and output. Same thing here. But it's a one resistor biasing. Or if you don't care about the Schrodinger drain and source, drain and gate, it's a zero resistor biasing that actually works. But as I said, normally you may have a resistor here too. If you do, you just add this to your equation and stuff. Right? So that's that. For integrated circuits, this guy is not very flexible. This technique is not very flexible, and there are two issues with it. One is that your options in terms of output selection are limited. The other issue is that RF is really large. Right? So if you want to separate the input and output from each other, you choose a large driver, 100K, 1 megaohm, 10 megaohms, depending on the situation. Such big resistors are, I'm not going to say impossible, but impractical when you're making an integrated circuit. For your integrated circuits, you make your resistors out of, let's say, 2-3 different layers in your whole process that we have 20 layers. So these layers have no resistivities, and the resistivities are not that high. So if you want to make a big resistor, you have to use a lot of that area. And it makes your device really large and therefore very expensive. So a common biasing technique for integrated circuits is to use a current source. So let's say if you know the ID that you want, instead of making it, establishing that ID using a setup like this H biasing network, you go and use a current source. So if you want a 10 micron current source, 10 micron ID, you put a 10 micron current source here, and you bias your device. If you want 100 micron, use 100 micron current source. If you want 1 million, use 1 million. And those current sources are tiny. Why? How do I make a current source? Diode is a possibility, but you get picograms of current. If I want 10 microns, then your diode is going to be huge. Go back to the same problem.
BJT.
A BJT or another MOSFET, right? So the current source, remember, a MOSFET is a controlled current source, so you can use it as a current source. So this, in reality, is something like that. So you have your RD at the top, your MOSFET that is doing whatever that you want it to do over here. At the bottom, you have another MOSFET, right? Which is biased at the current that you need for top guy. So this top guy is the one that has a requirement for the current, right? And the guy at the bottom provides whatever that top guy needs. If you need 10 micron, you get 10 micron. If you need 100 micron, you get 100 micron, right? So that's how we bias Any questions?
So then the bottom guy, if he's completely off, then nothing will happen, right?
Yeah, so the bottom guy sets the current, right? So if you want 10 micron, you bias this guy at 10 micron. And then the drain current of this is 10 micron, it forces it through M1. Any questions? Yeah, so it's a chicken and egg problem. So how do you bias this one now? So there is usually a bias circuit for your integrated circuits. What you do is that you go and bias a transistor over there. So in your bias circuit, let's say you use one resistor to bias a transistor in the region that you want, right? This is the biasing technique used. You already saw it. So you get whatever current you want using this biasing technique. You use one resistor to bias this. Okay? Once you've done that, you take the gate voltage of this guy and apply it to this one. Okay? So now you have the same VGS for these two transistors, therefore you should get the same current. Great, so this is called the current mirror. You establish a current here, you mirror it here. And if you have 5 different transistors that have to be biased at different currents, you take the same voltage and bias them with, let's say, M3 and M4 and M5 and all those other guys. Because the good news here is that your gate is not drawing any current. It doesn't matter how many of these guys you connect with, they're all saying the same VGS. If you want different currents, easy. You choose the W over L ratio for this whatever that you want, let's just call it alpha. If you want twice the current for M2, you choose this to be 2 alpha. If you want half the current for M3, you choose this to be half alpha, the W over L ratio. You change the W, right?
You wouldn't use a circuit like this for the triode region, would you?
You can, but why do you want to do that?
Wouldn't you only get the variable resistor if you could change the voltage here, but changing the voltage changes like the output current here, right? Don't you need
So these guys, you know, M2, M3, M1, or that dielectric device over there, they're all in active region, right? So you're always making sure that they are in active region, they are not. So if they enter into triode region, gate is still okay, gate will not know. But if the drain voltage here drops too low, this device may enter triode. And the problem with that is that then your bias current at the top may not be what you thought it was. It may be something else. It's going to be, now it's going to depend on VGS of M1. Right now it doesn't. Okay? So let's say the gate of M1 is something, you set the current through M2 that goes through M1. The source of M1 adjusts itself so that you get that current. But if you have a resistor for M2, then you will get some other current based on the value of that resistor. Right? So things will go out of hand. So you can use something like this to control the triode, a resistor in triode region, but I haven't seen that application. I'm sure somebody has done. Right? But for a biasing circuit, this is how you do it. So you create the biasing network here at the beginning of the process, create the current that you want here, establish the current that you want here, and then you just mirror it for all 3, 4, 5 stages that in different values of current. Interestingly, yeah.
And those that 2 alpha and 1 over 3 alpha, that's proportional to the current, like that.
Yeah. So if this is 2 alpha, then this ID is 2 of, let's say, I bias that we established here. Same VGS, right? And then this is going to be mounted on ID, I bias to ID, and so on and so forth. Right? So these are called current mirrors. And actually, so you don't see them in the street circuits that much because transistors are expensive in the street circuits. Integrated circuits, transistors are very cheap. So you can just make as many characters as you want and no problem. Same technique is done with BJTs. With BJTs, you have to be careful that the gate current is not well, the base current is not like gate current. You have some base current. So if you attach too many of these guys to your reference here, you're affecting the current here, right? Because you're drawing more and more current through that RD. The I base of those devices has to be supplied through RD. So you can account for it, but so therefore it is also very common for BJT integrated circuits to be biased this way. But for MOSFETs, this is almost the only way. So if you need the current source, this is your current source. This current source sinks current, right? Draws current from the node, right? If you want a current source that supplies current, you use a PMOS. So a PMOS circuit, when you look at it, so what I can do is, for example, I can extend, it's not as simple as this, but let's say you want to keep it simple. I can create also a VGS for my PMOS test and use that to supply current now. Not sink, but supply, right? And again, I can do the same thing that I did for NMOS as well. I can do the ratios of variables and else and get whatever current I want. Okay, and then if you look at, they don't show you the inside of the circuits that much anymore, but if you look at a BJT op-amp or a MOSFET op-amp, MOSFET op-amps were not around that they used to show you the circuit. You see a lot of transistors. Right? For a typical op-amp like 741, you see 30, 40 transistors. 25 of them are for biasing. There are only 5 that carry the signal through an amplifier. Right? So biasing actually takes a lot of time and effort to design, but it's relatively, there are a few modifications and improvements to this, but this is the concept. We create the current sources that we need to bias your devices, and you bias your devices. Okay. Any questions?
Can you find Kn in a data sheet?
Yeah. So if you, for example, again, it depends on the data sheet. But let's see. If you go to your labs, I think you have 27,000 in this lab. Sometimes it is stable. Right? So sometimes you can actually point to K value, right? But sometimes it's not. But what they give you is that ID for different values of VGS. Right? And if you have that ID for different values of VGS, they plot something like this for you in the data sheet. They say ID VGS looks like this. So this is the first one, this is the second one, this is the third one. VGS 1, VGS 3, VGS 3, right? And if you have that, you can calculate it because they give you the threshold voltage. The threshold voltage is given, and knowing that, you can estimate K.
Thank you.
Okay. But sometimes it's also given, right? On the first page, they show you K, and they usually say K. Instead of mu and C. They don't give you the details of the process. If they tell you mu and C ox and W over L, it's not so hard to find it about all devices, right? You can just open one up and do a Google investigation. But they don't want to give you that information anyway. And most users don't need it. Okay. So let's make amplifiers. So let's look at our NMOS and PMOS is going to be exactly the same. So like BJTs, the small signal model of a PMOS is exactly the same as the small signal model of an NMOS. So what we showed here, if I show you the small signal model only, there's no way for you guys to figure out if this is an NMOS or PMOS. It's the same VGS and the same GM-VGS, the same directions, everything is the same. So, we want to make amplifiers with this device. You have 3 terminals. We said your body terminal is usually left untouched for the signal processing applications. And you have your gate and drain and source. You have a signal source, you have a load. Signal source can be an antenna, load can be a speaker. Signal source can be a temperature sensor, load can be the input of an ATV, right? And we want to see what are the possibilities. And so, how do you do it for the So we have a bunch of possibilities. We can have the input applied to the gate, and the output taken from the drain to the source. We can have the input applied to the drain, and they can take the output from gate or source. And we can apply the input to the source, take the output from gate or drain. These are all the possibilities, right? You can apply your input either one of those terminals. For each one, you get 2 cases for the output. So, remembering or recalling what we had for BJTs, what do we never do in terms of connecting the source to one of these terminals or connecting the load to one of these terminals? Let's start with the load. What do I never do? Then I'm connecting the loads to one of these 3 terminals. Which one should I always avoid? Why gate? Because IG is 0. I'm delivering 0 power to my load. The whole point of having an amplifier was to have more power delivered to the load than is available from the source. So I never take the output from the gate. So this one is out, and this one is out. Okay? Okay, so I have 4 remaining combinations. Regarding applying the input, where do I never apply it? So the input is, I'm talking about sources of voltage sources, right? So where do I never apply a voltage source to? Gate, source, or drain? So think about BJTs. Which terminal we never used as the input terminal for your device? So with BJTs, which terminal was it that we never applied the signal? Collector. Right? So the equivalent for MOSFETs is drain. That's your current source terminal. Right? So if you apply a voltage source across a current source, nothing happens. It takes it, but nothing happens.
But drain and source are functionally the same.
No.
They are.
They have the same current, but from the drain end, if you look down, and we're going to do that calculation soon. If you look down, you see a current source. From the source end, if you look up, you see a small resistance. They're not the same. But regardless of that, from the drain terminal, from the drain end, you have a current source whose value depends on VGS. Okay? And therefore, VD that I apply here doesn't change it. If I ignore the channel length modulation, that's all. If you want to think about it that way, if I apply a input to the source and look at the gate, see the drain current depends on VGS, right? So if you apply an input to here, your drain current will change. You will modulate the drain current. So which one is it that you don't do? This one. Right? So I'm left with 3 possible combinations. They are actually very similar to what we did, what we saw for BJTs in terms of how they behave, the general characteristics. with a little bit of actually simplification because I have an open circuit here. So naming is similar, like BJTs, you had input to one terminal, output from another, it was common the other, common the third, right? So if you apply the input to the gate, take the output from the source, it's a common drain stage. If you apply the signal to the gate, take the output from the drain, it's a common source stage. And if you apply the signal to the source, take the output from the drain, it's a common gate stage. This is like common collector, this is like common emitter, this is like common base. We'll see that in terms of how they behave, general characteristics, everything. Let's start with a common source amplifier. I have a current source for my MOSFET to convert the changes in current into a voltage. We use the resistor and drain. And then, or we like voltages most of the time. So a resistor over there will transform the changes in IB into a current. I'm going to plug the resistor here from the beginning. We've done this many times. I could start with the RS of 0, but it's just too easy. Let's solve it for a case that RS is not 0, and then we set RS to 0 and see what happens to our equations. And this is my input. Again, the assumption is that the biasing is taken care of. So I'm only showing the signal. So somehow I have biased this at the current that I want, and it is in the active region. And I'm only focusing on the signal. So if I look at this circuit, this is my core CS stage, common source stage. Core meaning that I'm not including the loading here, I'm not including anything that we have behind the gate for biasing from the source, all of that stuff. I'm not showing you that. So if you want to analyze this circuit, you go and draw the small signal. At the gate end, well, let me draw the transistor first. At the gate end, I have my input signal. Between the gate and source is just VGS. Source bottom, I have RS. And at the drain end, I have RD that is now connected to ground because VDD is not changing. Okay? And that's it. That's my small signal equivalent circuit. What is V out? I start from what I'm interested in finding. So V out is minus GM/VGS times RD. And by now you know why it is minus GM/VGS, right? Because the current is coming from the ground, going up there. Okay, so that's good, but I want a relationship between V out and V in, and I have a new variable here, VGS. So I'm hoping to relate the two. What I can do is I can write a KVL in this loop, or in this essentially opened loop, because between gate and source we have an open circuit. So if I do that, V in is VGS plus IDRS. So V in is VGS plus IDRS. Right? And IB is this current. But that current is GM/VGS. So instead of volume with that, I just write GM/VGS RS. Okay? And I'm done. Because I can find VGS as a function of V from this equation, plug it in here, and solve. And actually I have the relationship between V out and V in. So right away, I can see that V out over V in, let's just, I'll do that here. V out is minus GM/VGS RD, so minus GM RD VGS. And VGS from this equation is Vn over 1 plus GMRS. And I divide both sides by Vn, and I have my gain expression. Okay? So minus GMRV over 1 plus GMRS. If you remember trigonometry, it is minus GMRC over 1 plus GMRE. Exactly the same equation. Okay? If the source is grounded, how? Maybe you don't have a source resistance, maybe you bypass it. Right? You can bypass, remember, you could bypass the emitter resistance, you can do the same thing here. You can bypass this source resistance. If you do that, then RS goes to 0, and you have your maximum possible gain from a common source state. So AV max or intrinsic, whatever you want to call it, AV max is minus GM. Okay? If I bypass it, if RS goes to 0, this is the gain I have for my stage. Negative gain can be reasonably high, right? So GMs can be on the order of millisiemenses and more these are kilos. So, you know, a gain of 5, 10, 100 even is not too difficult to get. Okay? So that's the first thing we wanted to know about this stage, the gain of it. What is, so this is AE. What about its input resistance when we're looking to the gate? So it's going to be resistance when we're looking to here. How much is it? Infinite, right? Because, you know, I can attach my test source and all that, but right away I say I'm drawing no current from that source. So regardless of the value for RS or anything else, Rn is infinite. Let me just write it here. Great. Great. It looks like that whatever you amplify with distance, if it is a sensor output, if it is a microphone output, if it is an antenna output, whatever you're trying to measure, the signal from the source, it will not even know you're measuring that signal. It will not even feel it, right?
Is that true for all common source stages?
Yeah. In here. In here.
It's true until he goes on the quiz and then puts it in.
No, I don't have to go into the quiz. This device is not going to work. This circuit is not going to work because it's missing all the biasing parts. Right? So as soon as you add biasing, as soon as you bias it with your H biasing thing, right? Well, what your source now sees is, whatever that is to the right. Over here it is infinite, but from here it is not. It's RG1 in parallel with RG2. There are situations, there are some circuits, some probes where the gate of the device is directly provided to you without any input impedance, without any biasing network. So what you can do is that you can bias this using your current source down here, not bother with that. Keep the gate voltage close to 0 somehow. Ask me how, I can tell you later. And you have direct access to that gate. And for that reason, the input current is going to be picons or femtons. Right? Your input resistance is teraohms or gigohms. Gigohms are the very least, but teraohms are high, right? And those are very special cases. Like what? Like you're trying to measure an electric field. You're not measuring the voltage anymore, you're measuring an electric field, right? Or there is a small capacitor, let's say few femtofarads. And so femto is 10 to the minus 15. And you want to measure the voltage on that capacitor without discharging it. Because if you drop 1 femtoamp here, the voltage across that capacitor is going to drop at the 1 volt per second rate. Before you, well, maybe there is enough time for you to measure it, but you're basically affecting whatever you measure. That's not something you want to do. But anyway, so if you provide a direct connection to FET, you get infinite practical input impedance. What's the danger? If I walk and touch that gate, what's going to happen? I'm going to be charged. This is a tiny device, you know, the gate capacitance for a discrete device. This capacitance here is 0 picofarads. For an integrated device, it's femtofarads, right? If I have 1 nanocoulomb of charge because of me moving on the carbon, 1 nanocoulomb, right? And this is 1 picofarad. I'm going to put 1,000 volts on that thing. This is going to get toasted, right? So if you're providing access to gate, you have to be super careful. So that's the ESD that you've seen on all the packaging, electrostatic sensitive, right? So that's why it is. Most of your circuits are limited MOSFETs. Input of those devices are gates. Gates are sensitive. And if you've touched them, and then the RAM still works, and then your CPU still works, and you say that these guys are idiots. That's not the case. Because they have ESP protection at the input of this device. And that's why the current is not 0, it's 1 femto. It's 1 pico. But that thing can save you up to the limit.
What would the R&D for a self-biased MOSFET?
Oh, the one from drain to source, the connection?
Yeah, when they connect the two.
Depends on RF and RD. We can do that as a calculation, but it's going to depend on RF and RD. So it's a combination of those two. But definitely much less than this. Okay, so R in infinite for the core stage, but usually you don't get infinite because you have bias. AV, GM, GM for a MOSFET is not as high as what you get for a BJT, but still, respectable. You can get probably half the gain for the same one current or something like that. And then let's just do R out and take a break. So for R out, what I need to do, R out is different. Now I need to attach my source to the output and see what happens. So R out is measured from here. If I do that, I have a new circuit because so far my source was attached from the left side, not attaching it from the right side. So I have to redraw my circuit. Now the gate, I remove that source from the input, it's grounded. I attach my test source here, Vx, and I measure Ix. Okay? The Vx over Ix is going to give me the output resistance that I see when I look at it from this point. Okay. What do you think it's going to be?
I think it's going to be RD.
Why?
Because the current going through the current source is controlled by the voltage across that is controlled by VGS there. VGS is going to be 0 because one end is connected to ground and the other is connected.
Yeah, so that's intuitively, that's right. You're saying that that's GM VGS. It doesn't look like VGS is affected by this Vx. So that VGS looks like it's 0. And therefore, all I see when I look back is just RD. You can do the calculations, right? So if you want, you can write a KCL at this node. Right? So Ix, the current that comes into the node, is equal to the two currents that leave, so Vx over RD plus GM/VGS. So we have this VGS that is annoying us. We have to find a relationship between VGS and Vx or anything else. On the right side, sorry, left side, I can write the k down here. So I start from 0, go back to 0. So 0 equals to VGS plus the current to RS is GM VGS times RS. Okay? So I have VGS times something is 0, RS is not 0, GM is not 0, so therefore VGS must be 0. And therefore up here this VG and VGS is gone, and your R out is just RD, which is VX over RX. Okay? Now, if you have that RO, the channel rate modulation model included, your R out is going to be a little bit more complicated, right? Actually, it's going to be significantly more. it's going to be what you have here when you look to the left, when you look at that current source. It's not 0 anymore because that RO provides a path connecting Vx to the VGS at the bottom here. And so if you have that resistor included, right? So now Vx, changes of Vx are going to affect the source voltage, therefore your VGS will change with Vx, therefore your GM VGS is not 0 anymore, right? So it's going to be a little bit more complicated. Look at it in your textbook. We are not going to cover that. It's going to be RO times 1 plus GM RS. RO will do more. But then. So, what can we learn about this stage based on these equations? I can have good gain. And then after break we go to an example. I can have good gain. Because GMs, if what I remember from BGT is right, it's millisiemens kind of value, and RD is kilo ohm type of value. So I can have some large number, minus 5, minus 10, minus 100. I can get voltage gain on this. Ra is infinite. I really like that. For a voltage amplifier, I want infinite input resistance, 0 output impedance, right? It's infinite. It's as good as it gets. Output resistance is RD. That I don't like that much. Because if I want to have a large gain, I have to choose a large RD. If I choose a large RD, I get a large output resistance. Okay? So same issue we have with the common emitter stage. It had high voltage gain, high input resistance, but also large output resistance. And we have to learn it by using other stages. And we need to do the same thing here for common source. So it does everything we like other than the output resistance thing. What is the current gain for this stage? So if I short the output to ground, and let's call this I out. What is I out to I in? Infinite. It doesn't draw any current. It can provide a current for you if you ask it, but it doesn't draw any current. For BJT, it was beta. The collector to base current, that was the ratio. Now it is gate to drain current. Gate current is 0. So it can have a huge power gain for you. Not so much voltage gain, but because of the current gain is large, a weak signal source, you can still extract information from. Okay. So we'll do a problem and one example after the break, and that's really it for common source stage.
Why did we do the first one then?
For what?
Because it's similar to the transition. And I just tried
The week, the end week
I was
Tuesday.
already thinking of this idea of, well, if there's no voltage drop,
Ah.
just apply it and there's no current. So,
Probably not.
this is zero voltage drop.
Rontographs.
Because,
Yeah.
well,
Rontographs? You don't know, it's like, nanograms times, femtograms are
there was like this is zero.
10 to the 30.
This is zero. This is zero. Which means that the only place where this could possibly be a voltage drop is if there's some voltage.
No,
You failed on this.
no, only because your girlfriend's freaking me out. No, she's freaking me out. Who's sending this? I'm like, are you sure? Yes, like, okay. Because I thought Gemini was
Break up.
she made me feel like we're not.
That was the easiest one.
This thing was
That's
so
the first one I've
easy.
ever got.
No, it's because she said consent. I was like, okay, consent.
For what?
We had a long talk about this. That's not acceptable.
This is pretty hard.
Watch me.
This is pretty hard.
Watch me do this. Yesterday actually made me feel good because I got the things right, but she made me fail.
Yesterday was so easy. Which she? What? Huh?
You want to understand? You're just shao brain. Let's go shao brain. Shao, shao. What's da brain?
It sounds more artistic now.
Yeah, I think you're right, man. I think you have.
You're like brain rot.
Yeah.
Wind very fiddle.
Depends on the muscle size, right? Because if it hurts when you touch it, then it's not hard.
Oh, you've been to the gym today? Yeah. Wait, I try break, so go to the try break. How long do you spend at the gym? A full school day. It's a 10-minute drive, not even.
I don't know, I'm trying to do
Exactly. Okay. Yeah, you lunch and you go for an hour and you go back here. You're just not efficient. Your break's probably what, 2 minutes long? Fuck a break, man. Nah, man. I don't need a break. I don't need a break.
The rest of the year,
Okay, you know,
see, I don't know about it.
this is probably a fake. This is a fake. This is a fake, I guarantee you.
No, I can't. I'm trying to do that.
Marvin closed? Okay, fill in the blank.
Only one starts.
Waters, Aries. Waters, Waters. There's titles, Aries. Front page, plot, king, wind, nature, wind.
I don't like being really happy for these verbs.
You should be able to get one. Two of them you can get.
Well, there's what's more than a quarter?
I think literally.
Yeah.
How much can you guys curl? Just one. It's like, oh, it's like dumbbell. Wait, you don't do that? Rex is the first set.
By the time we graduate the Berkeley,
8?
how much like electronics are we supposed to know, and like how good are we supposed to be at it?
By the time we finish this course, we have to be really good. After that, I don't know. Depends, it really depends, because you guys can do a lot of different jobs. And so if you look at our alumni, some of them are embarrass us, they are in data science business.
For systems.
Don't follow them. But they're good mechanical engineers from this.
That's
They're
me.
good robotics engineers.
That's me.
They're good I know people that went to Intel, they're doing firmware design and digital circuit design for Intel. A whole bunch of people went to Google and Microsoft and Tesla and all these other places. I don't know of any of our graduates that are analog circuit designers, right? But so in terms of what you, how much of this you may need, it really depends on which career path you choose. Right? So if you become a robotics engineer, if you get involved in the hardware side, your interface with the world, like anywhere else, is always on. Right? So even if you buy a sensor that is producing a digital output, you have to know what's going on inside that sensor, and that's an analog world. Your life is easy. Nowadays, a lot of these sensors do provide digital output. So you buy an accelerometer that has a I2C output, right? Or you buy a pressure sensor microphone, your microphone can provide digital streams of the output. So in those cases, life is easy. But easy means what? Anybody can do it. If anybody can do it, you don't have a market or a corner of market to yourself. As soon as you develop something, somebody else can just come and do a better job on the software side, or make it cheaper than you, and then you lose that share. So when you want to push limits, you have to deal with the physical. The digital sensors, there are sensors out there that have digital outputs and they're easy to use, but usually you get the best performance out of the ones that have an analog output. And they are not necessarily old sensors. Because as soon as you do digitization, so I'm forcing you to accept whatever resolution the A2B provides. 12 bits, that's all you get. 14 bits, that's all you get. The sensor may provide you with much, much higher resolution, right? So if you need that extra 6 bits of resolution, you might be better off to get an analog output from the sensor, or maybe sometimes directly interface with the sensor. You're measuring capacitance or inductance or light intensity. You might want to directly interface with it rather, because let's say for a sensor you have something, a transducer, something that transforms pressure in this room into a change in capacitance, right? Or the amount of light into this room, into a current. Or so for LVDT, the displacement into an inductance change, right? So that's the transducer part. There is an interface circuit that is always on. That thing cannot be digital. That converts that changes in whatever your transducer produces, the capacitance and the current voltage, whatever it produces, charge, and converts it into a voltage or current that you can easily use. Right? So let's say it can be a microphone with a very high output impedance, and A2B cannot beat this. But you have this interface circuit between that high output impedance capacitor microphone and your A2B to make the impedances match, or make it easier for you to do. So that thing is always on, right? And after that, you may have your A2B on chip in your sensor package, or you may have your own A2B. If you're pushing the envelope, you should be able to do a better job than the generic interface circuit, and you should definitely do a better job than the generic A2B that they have on these boards, right? So if you're interested in measuring I don't know, so in my lab, we are measuring the changes in gravitational forces. Okay? But we're looking at the 6th and 7th and 8th digit of change, not the first 6, not the first 5, right? So we're looking at nanogs of change, right? So in that case, it's actually a bit of a funny different situation, because if the sensor doesn't exist, we have to make the sensor, we have to make the circuit, and we have to make the A2B board and everything else. But anyway, it applies to a lot of cases. If you're pushing the limit, and your limit is sometimes bandwidth, in many cases it's noise. Whatever that is generically packaged and provided to you is usually not enough. Or it may be super expensive, because somebody may package that pressure sensor with a 32-bit A2B or 24-bit A2B, but that may be $1,000 pressure sensor now, and your customer or your project can only assign $100. Then you go and pick a $20 A2B that is 24-bit A2B, guaranteed to perform as the data sheet says. You put your super low interface circuit between your A2B and the transducer, and then Then you have a market corner. This is design, because others don't have this circuit. And if it is really important to you, you can go and have it. Those kinds of things sometimes, depending on the situation, can happen. So now you have a corner of the market to yourself. For a while. Then you have to repeat this thing again. So in analog, it's always about, are you dealing with real world or not? If you're dealing with real world, are you pushing the limits or not? Because if you're somewhere happy and mellow, you know, go and do forward. Everything is more colorful. But it's not true. And the issue, so one of the other things that my analog, so my students or generally analog circuit designers have is job security. They are not replaceable that easily. Because, you know, what you see here, everybody goes through this, it doesn't stick. For this stuff to stick in your mind, you have to practice, you have to make a few circuits, you have to make a few mistakes, right? And then, it's kind of a knowledge that you cannot study, it's just like black magic that you have and others don't. You can learn from better people, more experienced people from you, but a lot of it is just so minor that you don't find them in any textbook or anything, right? And therefore, if the company loses you, they're losing knowledge. And they may not be able to get that back because the next person that has developed, you develop this device for this product, this circuit for this product, you know everything about it. You have figured out the parasitics, you have figured out the noise limits, you have figured out the temperature variations, all of those stuff. A lot of it is not documented. If they lose you, they lose all that knowledge. So usually, you know, the CFO and CTO may go before the analog circuit designer.
So are you saying that we shouldn't document anything?
Depends on how replaceable you are. If you are replaceable, yeah, make sure you document things, don't give them another excuse. If not, then you're the boss. Anyway, so let's go back to this. Analog is more difficult, you know. I don't know how much digital you know, but life in digital world is easy. Life in software domain is much easier. You get what you want, right? In here, you have to battle physics. You have to battle gravity. You have to battle temperature. You have to battle light, right? So it's always challenging. There's always, I find it more engaging, more interesting. So, in 2-3 years, come to my lab. Our noise limit for some of our circuits is 0.2 electrons. So the signal to noise ratio is 5 times better than what you have for a single electron. Anyway, but that makes it interesting, right? Okay, so here is an example. This is our common source stage. Input applied to the gate side, output taken from the drain side. Okay. And this is a design problem. So I actually have to check my notes for this one because if I do it different, I'm not going to get the numbers played. I think I read it for whatever I'm going to teach you. But the requirements are, the gain has to be -5. It's not a high gain, doable. R in should be 50K. Okay, so I look at this circuit and the input resistance when looking into the gate is infinite. Well, that puts a condition on RG1 and RG2. That's okay. AV -5, not a big number, should be doable. P dissipation, the power dissipation should be less than 5 millivolts. So if I want to calculate the power dissipation for this circuit, it's how much current I'm drawing from the supply times the supply voltage. Right? So I have IB on the right side and let's say IGG on the biasing side. Let's call this IGG. And call this IB. So the sum of these two currents times VDD should be less than 5 millivolts, so that's again relatively clear. And VRS is 0.4 volts. That's a requirement you usually don't have. You have to decide. But so that we narrow down the solutions or the options, we have a number for VRS. How much voltage I want to put for VRS? One note before we move on, why do I need an RS? Similar to BJT circuits, this RS helps your bias plate become more stable. Okay? So similar to the common emitter with resistor in the emitter, this resistor in RS, well, if for whatever reason your ID wants to go up, if ID goes up, IDRS goes up. If IDRS goes up, your VS goes up. If VS goes up, and assuming VG hasn't changed that much, your VGS decreases. If VGS decreases, your ID goes down. So you have that negative local feedback, right? So it helps you get a more stable bias current. How much voltage you assign across RS for BJTs? We said 0.2 is a good number. If you can afford it, maybe 0.5, but maybe not less than 0.1. For MOSFETs, it's not as clear because you're trying to usually battle the changes because of the VTH. VTH, the threshold voltage changes, the temperature changes from device to device, all these things, and they're usually more significant than VTHs. So, having half a volt here, 1 volt here is common. Okay, so this is the problem. When you have the device specs, integrated device, so I can choose the W wherever they want. Threshold voltage is half a volt, VGT is 4.8, and nuance outside is 100 microns per volt squared. So let's go and see what I can right away fix. So P dissipation has to be less than 5 milliwatts. So from here I see that ID plus IGG, the current that comes from the supply goes through the biasing circuits, biasing resistors, times VDD has to be less than 5 milliwatts. I have a number for VDD, 1.8 volt. I can see that ID plus IGG has to be less than 2.78 milliamps. Okay? And IGG, I can control it. So I want to have a 50 kilo ohm input resistance. If it is 100 kilo ohms, if RG1 plus RG2 is 100 kilo ohms with a 18 volt, 1.8 volt power supply, that's 18 microns, right? So what I'm going to do is that I'm going to leave a little bit of safety margin here. I'm going to need 20 microns later on. Okay? So I'll leave that much up. Choose ID to be 2.7. This is a design problem. You can choose 2.5. I'm pushing it to the limit because if you choose, let's say, 1 milliamp will satisfy that requirement, right? You will have even less than 5 or 3 milliamps or 2 milliamps. If you choose a small ID, what is the price you pay? Or what is the price you pay?
Less application.
GM. Right? Small current and small GM. So if I'm allowed to use 5 milliwatts, I pick a current that lets me stay within the limit, but relatively.
So you're just making an arbitrary decision on what proportion of that 2.78 milliamps is ID versus IG. Is that correct?
So what I'm saying is that for IG, because look at RG input resistance, is RG1 in parallel with RG2, right? So it has to be 50 kilo ohms. I'm going to just make an assumption. It's 100 kilo ohms in parallel with 100 kilo ohms, right? Or something like that. So the combination of RG1 and RG2 is on the order of 100 kilo ohms, 50 kilo ohms to 100 kilo ohms. So that requires about 18 microns. I need more than enough for that. So that's 80 microns that I'm setting aside, giving the rest of it to ID. There are more than one solution, right? It's a design problem. We can choose 2.6. You can make it work with 1 million. But we'll see, what the implication will be. Okay, so if that's the case, then I know the gain of this stage is -5. I want to have a gain of -5 because I'm bypassing RS. GM1D is 5. Okay. Actually, right away, because VRS or VS is 0.4 volts, I can find RS. Okay. So I've already found one component. I need to find RD. So GMRD is this much from the question, and because I know ID, I have a couple of options for choosing the gate source voltage. So GM equation that I'm going to use is 2ID over VGS minus VTH. So that's GM. That's one of the three equations that I could use. Times RD is 5. Okay? Why do I like this one? Because this doesn't have W over L in it. I can choose VGS, and it's a design problem. Okay? The other two equations have W over L in it. So I have to make a decision for W over L and then proceed. But this one, I make a decision for VGS. Okay. So if I choose VGS, and then actually there is a better choice. So if you choose, yeah.
Oh, did we set GMRD to be 5 or like how did we do that?
Sorry?
It's in the question. GMRD.
So AB is minus 5, GMRD. The gain of this stage is the common source stage. The gain of it is GMRD. Or minus GM. You can choose another equation for GM. You could also find GM from this equation. Right? 2 mu n Cox W over L. And because you've chosen ID, you could choose something for WL and come up with a value for Q. Different ways of doing it. I'm going to do this because there is a point we want to make by solving this example.
And is the 2ID over GS minus VTH, is that a common equation or just like special to the circuit?
No, this is one of the equations. One of the equations you can use for GM. So that's the other one, and the last one is this one. So 3 equations equivalent.
Alright, thank you. Nice.
So you can find GM from this equation, or this equation, or this equation. The 3 of them are the same thing, because the device is an attribute. Right? I'm using that. And if I want to have, so I still have 2 variables here, VGS and RD. It's a design problem. I have to choose values and move on. I choose VGS. So, assuming if VGS is 1 volt, then VGS minus VTH, I know VTH, I have no idea I have GM. Okay. And because GM is this much, then RD becomes 5 divided by 10.8 milliseconds. And that's 463 ohms. Okay? So I have my RD, I have my RS, RG1 and RG2 are fine. But for the device, I still haven't decided on W over L ratio. Okay? Because that's another unknown in this problem. So I go and pick, why I actually don't go and pick, because I already know device is an active region, it's 1/2 mu n Cox W over L times VGS minus VTH squared. This is the equation, this is the relationship between current and voltage. ID is 2.7 milliamps. I chose VGS to be 1, VTH is given, these guys are given. After that, I have a W over L ratio. Yes.
Go ahead. I'll pass
Okay.
after.
So when we're calculating GM, we make one assumption, which is VGS is equal to 1 volt.
No,
Right?
We didn't assume, we assigned.
Sorry, you assigned, right?
Yeah, let me fix that now.
Right here, this is GM.
We do not, yeah, so we assign,
Oh, that's what make GM.
Just finding GM first.
it's a design problem. You have that flexibility. So,
Never mind, yeah.
The denominator there is VGS minus V threshold, that is GM, or that whole fraction, right? The whole fraction, right?
ID over, 2ID over VGS minus VTH is GM.
Okay.
IDD is really small.
Okay, so from this equation, I didn't know W over R. I can find W over R and I'm done. Okay. Am I done? So did I finish the design? Forget about RG1 and RG2. What should I do next? Well, so RG1 and RG2 I have to get, but let's stay on the gain side. Am I done? I calculated ID and VGS such that I get the gain that I want, and I chose W over L such that I get the GM that I want. So it's like, it's all good. Anything that can go wrong? So far, I'm assuming the device is not complete.
Well, let's check
It may not be. Right? I'm hoping it is. It may not be. So you need to check. You need to check. And with these numbers that I have, will it stay in active
But
use?
it might be different value.
Or will it be in active use? So what I need to do is that I need to calculate VG. Because VGS is done. VGS, I assigned VGS 1 volt larger than the threshold voltage, 0.4 volts at the source. All of that is easy, but I need to calculate VGD. So VGD is VG minus VD. VG, in this circuit, I have 0.4 volts here, I chose 1 volt here. So VG is 1.4. Minus VD. VD, like the million circuits we've seen so far, is VDD minus IDR. And if you do the math here, VGD is going to be 0.78 volts, which is larger than V threshold. So the device will be in trial duty. Right? So you push it into trial. You need this to be less than V threshold, but this is larger than V threshold, which is half a volt.
Oh, active is when it doesn't matter about what does it care about that one.
It depends what we want. Does it want
I guess active is
yeah.
Okay? So how do I solve this problem? I chose, yeah.
Well, could you not choose a different VGS then?
That's one way to do it.
Since it
What will it do? So VGS, what is the problem? My VG is too hot, right?
Yeah.
So maybe I want to bring it down. So let's say we can choose the VGS of 0.7. And 0.7, and you go through the calculations and everything else.
I might change that.
What else can I do? So that's one way. We can bring VG. What else can we do?
increase RD.
I increase RD, you bring VD further. We want to bring VD up. Right? So either we reduce VG or increase VD. Right? So let's do that. That's one way you can do it. The other way is to increase VD. if I want to increase VD or my current is fixed, my only option is to play with RD. So I reduce RD to half of its value. And then these numbers is just because I have notes here, you can choose one of these. So I have to follow this so that you don't have to do all of the calculations. It's a design problem. So I choose RD, let's say the new RD to be half of whatever I had before. Okay, so it was 416, now it goes to 230. My GMRD was 5. With this new RD, I need to have a new GM. Okay, so instead of 10.8, because GMRD is constant, I reduced RD, I have to compensate by increasing GM. New GM is 22 milliseconds. If I don't want to touch VGS, all I need, or all I can do is not play with WFF. I can make the device wider. So, do what we did before and you get a new WFF. Right? So you make RD 2 times smaller, you have to make GM 2 times larger, right? But because GM is proportional to the square root of RD, you have to make the WFF 4 times larger, because it's square root of WFF, right? So I go from like 216 to 89. Why is it not exact? Because I'm using 230 instead of 463. But almost 4 times as big. To get this twice the GM for the same current, I make the device 4 times as wide. And then life is going to be fine now. From this point onwards, what you have is you can see that your VGS is now going to be 0.745 volts, and therefore your VG is 1.145 because we still have the 0.4 volts across VS, and therefore your VD will be 1.18, and between these two you can see that VGD is 27 volts, 27 volts, which is not less than VTH. And we are happy in the active region. So with these conditions, we get the gain we want. We need to go and decide on RG1 and RG2. That's the relatively easy part. So first thing I notice is that VG, the gate voltage I need is 1.145, right? So that's the voltage division between these two resistors and VDD. Okay? So that's the voltage division I have. I have two unknowns. I have RG1 and RG2. I need to find another equation. Another equation comes from RN requirement. So RN has to be 50 kiloohms, and that's RG1 times RG2 divided by RG1 plus RG2. Right? And from these two, you can go and find RG1 and RG2. Easy thing to do is to divide this equation by this. And right away you get RG1 back.
No, just RG2.
Okay? So the whole point of this exercise, we did a little bit of DC calculation here, but the whole point is that when you're designing you need to be mindful of the bias. You need to make sure your device is in active region. You need to make sure you have enough headroom for whatever voltage swing you're targeting. So usually start your design from the AC side. They give you a gain, input resistance, output resistance. So that's the AC parameters that you have. You go and choose your DC parameters to make sure that they meet the AC performance that is needed. But you also want to make sure that your device is heavily biased. In active region, that means. So, solve a few circuits with the small signal equivalent circuit for each almost. So in your assignment, you have a couple of problems like that you have to go and write a small signal equivalent circuit and solve it. But then after that, after you solve your first 200 problems, you can go and use formulas. Right? So if you can reduce the circuit to this core common source stage, you can use the formulas you already know. You say, looking into the gate, I have an infinite resistance. You now add the biasing that is before it to find that the input resistance behind the biasing network. If you want to find the gain, it's GMRD or GMRD over 1 plus GMRS, the negative sign. So if you can reduce your circuit to this, what you have at the drain of this device is RD in parallel with the input resistance of your next stage, right? Whatever it may be. But then put in for RD here, and RS is whatever you have in the source of this device. Maybe parallel with some other stuff, maybe not. But RD and RS are the resistance, effective resistance, or equivalent resistances you have in the source circuit, in the drain circuit. Once you calculate them, use the formula. And you can analyze the circuit more quickly. We have a common drain stage. I want to talk about it in 5 minutes. Or source follower. So for common collector stage, they call it emitter follower, a common drain stage, which you should be able to tell me how it looks like. Signal goes to the gate, comes out of the source. And PMOS is exactly the same. So this is a common source stage. Let's very quickly find out
Common drain.
what's the input resistance.
Wait, is this common source or common drain?
Common drain. Right? Because signal goes into the gate, comes out of source. It's common drain.
Okay.
Right? Common drain. What's R in? Infinite. No need to solve.
You want me to review? Want it? Little. Come on.
We already have done this calculation. So what is V out? V out. I'm going to run through this calculation because we've already done it. GMVGS RS. Right?
Yep.
The current that goes through RS. And I have the KVL on the input to relate V in and VGS. Combine these two with each other, you get your gene expression. So it's like the common collector stage we had before. It was GMRD over 1 plus GMRE, this is GMRS over 1 plus GMRS. Difference, it's even nicer than the common collector stage because my input resistance is infinite. Right? Common collector stage, we used it when we wanted to connect a high impedance impedance source to a low impedance load. Right? So it had that low output impedance as well. Let's see what we have here for this one. Give me this load. See, you can see. I attach my test source to when I'm looking for the output resistance. Right? This is output resistance. Vx and measure Ix. I read the KCL at this node. And gauge is grounded. So KCL at that node. Ix that goes in equals Vx over Rs, this current plus this current. This current, nothing goes to the left. On the right side, I have minus GM VGS. Right? Okay, good. I have VGS that I don't know. What is VGS? VGS is negative Vx, right?
Okay.
Or magnitude. Vx over Ix is going to be I already, I'll show it to you how it looks like easy in the case inside. So it's 1 over Rs plus GM, right?
Minus?
If I plug minus VGS, and
Oh,
this is
minus.
VX, this is the expression I have. This is two resistors in parallel. One resistor value is Rs, the other one is 1 over GM. So it's very common to write it that way. So this is telling me that Vx over Ix, or R out, is, we can write it as this 1 over GM plus Rs, 1 over Rs. Or you can say 1 over GM is millisiemens, it's conductance. 1 over GM is the resistance. So 1 over GM in parallel with Rs. Okay? And this is very common. So you see in a lot of equations that they treat 1 over GM as a resistor value. And they put it in parallel with this. And because just the equations will be really look nice. Is it a large output resistance or a small output resistance? Small. Right? Because GM you're talking about, millisiemens, and 10 point something. This can be 40, 50 ohms. And RS really doesn't matter. If it's a kilo ohm in parallel with 50 ohms, it's 50 ohms, right? So this guy can give you small output resistance. These are our two favorite stages. The last one is common gain. It gives you a high gain, but has a low input impedance and a high output impedance, like a common base stage. So typically it is not used. And in low frequency applications, it's not used. Right? It has its own applications in high frequency, but low frequency applications, common source and common drain and effects. Okay? And that's MOSFET amplifiers.